SwayamPrabha. Digital India. Educated India.
So, in this lecture, we will discuss some non-equilibrium molecular dynamics simulations. So far, our discussion pertained to equilibrium MD simulations, where we would specify Newtonian as a sum of kinetic energy and plus potential energy, and then use Lagrangian equation of motion or Hamiltonian equation of motion, and then we show that in such a equation of motion, the trajectory follows such a way that the energy is a conserved quantity or it's a constant of motion. So, for example, when we do NVE simulation, which is corresponding to an isolated system, the system reaches a equilibrium state which corresponds to maximizing the entropy when you constrain the energy and volume and number. So, with the NVE ensemble, by simply solving Newtonian mechanics or Hamiltonian mechanics in a classical framework, basically ensures the system will reach equilibrium provided that you run the simulation long enough. On the other hand, even if you want to constrain temperature and pressure by coupling the system to a external bath, thermal bath or pressure bath, where through the boundaries the system is able to exchange energy or it can do work, we still see that such a system will also preserve equilibrium when you run the simulation long enough. So, when we say equilibrium, what we mean is whether it is NVE simulation or NVEs, we say that there is no net thermodynamic flux. Okay, so there is no net flux going across the boundary G, but then if you wait long enough, all these systems will reach an equilibrium state. So, all our discussion so far is about the conducting simulations so that the system reaches an equilibrium condition, and then we were worried about calculating the equilibrium averages and sometimes even transport coefficients also. So, now we would like to go to another domain which is known as non-equilibrium MD simulations, and the reason why we want to do non-equilibrium simulation, there are two motivations. One is we would like to improve the accuracy of transport coefficient calculations. So, here we are talking about viscosities, diffusivity or thermal conductivity, etc. So, if you look at our previous discussions, we looked at even equilibrium MD simulation can be used to calculate these transport coefficients by calculating transport time correlation functions. For instance, the diffusivity is related to the velocity autocorrelation functions, and then shear viscosity is related to auto. So, even able to use equilibrium MD simulations and calculate time correlation functions, and then integrate the time correlation functions to calculate diffusivities and viscosities and etc. There are some inherent problems with this approach. For instance, these time correlation functions are typically subjected to large statistical errors. In our previous discussion, we talked about systematic and statistical errors. The statistical error comes about because of the finite length of the simulations, and we looked at how even then the amount of errors of the calculation of time correlation functions are quite large. Mainly this is because we depend on natural fluctuations happening in the equilibrium simulations to calculate the time correlation functions, and these are very small fluctuations. So, the error involved could also be quite high. In other way, you could say that the signal to noise ratio in calculating these fluctuations and time correlation functions are quite unfavorable, and often we work with a very small and there is a time scale that we can reach in calculating correlation times is also limiting. Okay, so sometimes if you are interested in a long time correlation calculations, then using this equilibrium fluctuations is quite limiting. So, these are some of the limitations of using equilibrium MD simulations to calculate time correlation functions and through which the calculation of transport coefficients. So, instead of this approach, we would like to basically do a non-equilibrium MD simulations, and in that non-equilibrium MD simulations, we will try to get the transport coefficients, and these estimates are quite accurate and more reliable and easy to do. That is one motivation. The other motivation to study non-equilibrium MD simulation is to look at the behavior of the system for a larger perturbations. So, when you apply an external heat flux or momentum flux and you want to look at how the system responds for an external perturbation, we would like to conduct non-equilibrium MD simulations. So, these are broadly two motivations to look at non-equilibrium MD simulations. So, now we will talk about some characteristics of non-equilibrium MD simulations. What is the principle behind it? How we are going to do this? So, in a non-equilibrium MD simulations, we look at steady state response of the system when you impose a perturbation. So, we apply a perturbation and then look at how the system respond to it, and we are looking at that system's response in a steady state behavior, and the steady state response can be obtained in the same way we used to measure time averages of equilibrium quantities. So, what that means is when you do a equilibrium MD simulations and let us say you want to find out equilibrium pressure, and what we do is we conduct an MD simulations under equilibrium conditions, let the system equilibrate, and then during the production run we do a time average of the pressure for the equilibrium value of the pressure. The same way, when we want to find out what is the steady state response for a given perturbation in a non-equilibrium MD simulations, we still look at the long time behavior of the steady state response and then do a time average of that response to calculate in non-equilibrium MD simulations. And if you look at the way we conduct this non-equilibrium MD simulations, it pretty much closely resembles the experimental system by which we study a physical phenomena. That for example, let us say you want to conduct a steady shear simulations. That means you have a plate, and then let us say there is a fluid between these two plates, and the top plate is actually moved with a particular velocity v, a constant velocity of v. Okay, so this is a very typical Couette flow experiment that we do to measure viscosity. In such a geometry, the gap L is typically very small, and then this velocity profile here is basically a linear profile. So, now if you want to conduct such a, if you want to measure viscosity in a computer simulations corresponding to this experiment, the simplest thing you can think of is you take a simulation box, keep the bottom simulation box fixed and move the top simulation box face at a particular velocity v corresponding to experimental conditions. So, it is possible to do that, but then you will see when we do such a framework, we know that we will have a problem with implementing periodic boundary conditions, because that if the particle is trying to hit the topmost or the bottommost plane, it has to reflect, and that becomes an artifact because when you do simulation, we are not mimicking the bulk system, but we are taking a very small system size representing the system's bulk behavior. But then by providing this moving walls on the top and bottom, moving walls at the top and then stationary wall at the bottom, it gives artificial surface effects, and it also violates the way that we do periodic boundary conditions. So, we cannot simply mimic the way we do experiments in the MD simulations by moving the top wall and fixing the bottom wall. Rather, what we are looking for is a proper non-equilibrium MD simulation should have a periodic boundary condition compatible. So, even the external perturbation that we are applying should be able to preserve the periodic boundary condition that we use, and then we also make sure that the translational invariance and periodicity of the system is preserved. So, these are some of the requirements we have to think about before we conduct a non-equilibrium MD simulations. So, now what kind of perturbations we typically do? There are different kinds of perturbations you can do to the system. One is the step perturbation. What we do here is at time t equal to 0, you give a perturbation and then keep the perturbation at the same value for a long time. Okay, the system is given a stepwise perturbation, and then once you apply this perturbation, then you look at the system's response as a function of time from time t equal to 0 onwards. And typically what happens is the response that you measure for such a step perturbation would be proportional to the integral of the time correlation function. And then the transport property can be related to the long time behavior of the response that we measure in this step perturbation. So, this is one type of perturbation. The other type is a pulse perturbation. That means at time t equal to 0, we give a very short pulse of a perturbation, and then we look at how the system respond to the pulse perturbation. So in this case, one would find that the response is actually proportional to the time correlation function itself. Then the transport property can be obtained by integrating the time correlation function with respect to time 0 to infinity. And then there are other kind of perturbations. For example, you can actually give a sinusoidal perturbation. So basically the perturbation can actually be an oscillatory behavior, and then you can measure the response and then take the real and the imaginary part of the Fourier components of the time correlation functions, and then from there we can also relate the transport coefficients or transport properties. So now we will specifically talk about one particular non-equilibrium simulation which involves doing a cuvette flow on a system. This basically means, like I said before, that you have a fluid and that is kept in between two parallel plates, and the bottom plate is fixed and the top plate is moving at a constant velocity v, and then there will be a shear rate in the fluid gamma given by dvx by dry, which is nothing but v by L. Okay, so that's basically the slope here. And then we can use Newton's law of viscosity to find the viscosity, because when you do an experiment, what we do is we move the top plate at a particular velocity and then measure the stress using some instruments, and then we know what is the shear rate, and then we know that we measure the stress, and from here you can calculate what is the viscosity. And in the non-equilibrium simulations, we are trying to do something very similar, very analogous to how experiments are done. So in order to do that, we are going to use something called this Lees-Edwards. So there is a Lees here. Yeah, Lees-Edwards boundary condition method. So this is third, where the boundaries are adjusted such a way that we would like to and then measure the response. So when you do this, there are two things we have to worry about. One is how do we measure the stress in the simulation, and it can be measured by looking at the steady state long time response of the stress tensor in the y-x component as t tending to infinity. That means we are talking about that once the system reaches a steady state and you wait long enough, and then you measure the equilibrium average of the y-x component of the pressure tensor and take the negative sign of that is going to give you the stress. The second thing is how do we impose the shear rate in the MD. That means how do we establish this kind of a velocity profile in the simulation box. So to do that, we are going to use this Lees-Edwards boundary conditions, and in this approach, you look at this periodic boundary conditions that we talked about before. That means you have a central simulation box, and it is basically replicated. The same simulation box is replicated throughout the space, and it's basically all these neighbors are basically the images of the central box itself. And we do that because whenever from one side, the images from the other side would enter. That's how we implemented the periodic boundary conditions. So now for the non-equilibrium MD simulations, especially if you want to apply a shear, we are going to use this Lees-Edwards boundary condition, which is basically a slightly different way of doing the periodic boundary conditions. So first of all, the infinite periodic system is subjected to a uniform shear in xy plane. So xy plane basically means the coordinate system is given here. So what we are seeing is this xy plane. So the horizontal axis x, the vertical axis is y, and we want to apply a shear in this particular plane. Now in this the shaded area here, this is basically the central simulation box. So the shaded square here, that is the central simulation box, and we store the particle positions and velocities of all the particles in the central simulation box. Then it has this neighbors A, B, C, D, E, F, G, H, etc. Now the layers along the central simulation box will be kept stationary. That means this E, the A and other neighboring boxes, these are kept stationary. They are not moving with time. So the top images, the top periodic images B, C, D, these are allowed to move at a speed of gamma L. So, remember gamma here is the shear rate, and gamma times L will be the velocity with which these top simulation box image boxes are translating from left to right, whereas the bottom images, that is F, G and H, these are moving from right to left at the same velocity v equal to gamma times L. And then of course, we are talking about the closest images, but then if you look at the images on the second layer of the top and the second layer at the bottom, they would be moving at much faster rate, because they are the farther they are, faster they will be moving. So, by doing this kind of moving of this image at the top and the bottom in opposite directions, we are basically trying to establish a velocity profile of this kind, right. So, so that is the main features of this Lees-Edwards boundary conditions. We keep the central layer fixed, top layers are moving from left to right, and the bottom layers are moving from right to left by the same velocity or by the same speed gamma L, only in the positive x directions and the negative x directions. So, now we basically have to look at how, if the particle crosses the boundaries, how do we ensure that we maintain the periodic boundary conditions. So, if you recall, for the equilibrium MD simulations with the periodic boundary conditions, if the particle moves from the central to the top, its periodic image will come from the bottom. Similarly, if the particle leaves to the right side of the simulation box, an image will come from the left hand side, and vice versa. But in this case, because there is a relative motion of the periodic images at the top layer, at the bottom layer, we have to take care of how to adjust or how to assign the particle positions whenever there is a boundary crossing of particles. Now, we will start with the simplest thing. Suppose if there is a particle in the central box moving to A, okay. So, that means there is a particle that is moving from central box to A. In this case, its a periodic image from E will enter from the other side, because E, A are not moving with respect to the central box. So, it would be like a very traditional way of doing the periodic boundary condition. And same thing, if a particle actually moves from the central box to E, its periodic image will enter from A to from the other side. So, applying periodic boundary condition in the central layer is unchanged. The procedure is unchanged. On the other hand, if a particle if the particle moves to the top, then it has to come from the bottom, but then the top layer and the bottom layers are moving at different directions, because of the fact that we want to impose a shear in the system. So, we want to make sure how to assign the particle positions when they cross the boundary, either at the top or at the bottom. So, to see how it is done, we look at certain formulas so that we can derive how to adjust the particle positions and velocities whenever they cross the boundaries at the top and the bottom. So, now in the laboratory frame, we can say that every particle I velocity has two parts. So, what we are talking about is that if I look at any particle in the central simulation box, its velocity can be written in terms of two parts. One is the thermal or the peculiar velocity. So, this thermal velocity comes because of kinetic energy and the intermolecular interactions, and there is a streaming velocity which is coming only because of the applied shear through the boundaries, and that velocity depends on the shear rate times the y position of the particle I in the x direction. So, that is the streaming velocity that happens only on the x direction, and that depends on at what height, at what y length scale the particle is at. So, then we can write the velocity of the particle, that is Ri dot, has two parts. This is the thermal or the peculiar velocity in the absence of shear, and then this is a streaming part that comes because of the shear. Now, at time t equal to 0, then all the simulation boxes would be, so at time t equal to 0, you will have the central simulation box, this is A, this is E, and this is C, this is B. So, at time t equal to 0, all of them are actually in the same place, F, G, H. So, at time t equal to 0, you are expecting a configuration like this. But then as time goes on, then all these boxes are moving from left to right and all these images are moving from right to left. So, this particular configuration that is shown here is at some time t. So, we would like to see as time progresses how this velocity changes for the particle in the central box as well as the particles in the images. Now, in this example, at time t equal to 0, we see that the particle position in, of the ith particle in C box, that is here, is given by the particle in the central box plus y times L, because that is right on the top. And you can see that the image in the box C is different from the position in the central box only by the y component, because it is in the positive y direction. Similarly, if you look at the same image at the G box here, then its position, that is the particle I's image in G box, will have the position Ri minus y cap L. This means that the particle I here and its image in J will have only the y component subtracted by a unit length of L, which is the box dimension. Similarly, the image in C, the particle in image C would have the y component added by L amount. So, that is so we can easily relate, if I know what is the image and where is the image located, we can identify what is the position or the coordinates of ith particle in those image boxes. Okay. So, this is something we know. So, now what we are going to do is we want to basically look at after time delta t, what will happen is these boxes are now moving. The central boxes are remaining constant, they are not moving. The A, the central box and E, they are not moving, but the top layer and the bottom layer are moving. So, we are going to write an expression to see how the particle positions and velocities changes as time goes on. So, at time delta t, what we do is we basically integrate this equation where the velocity was written in terms of peculiar velocity and the streaming velocity. So, let me write here Ri dot was Ci plus Ui, which is nothing but Ci plus gamma Ryi x cap. So, this is the velocity of particle I in the central simulation box. So, now we will take a very small delta time t and then we integrate this equation over the small delta time t. So, you will see that the position at time delta t, this is actually delta t, would be initial position plus Ci times Ci plus gamma Ry x times delta t. Okay. So, this is over at small time delta t, this would be the new position. So, then we basically expand this. So, this is the initial position, this is Ci times delta t, this is the displacement because of the thermal or the peculiar velocity, and this is the displacement because of the streaming velocity. And now we can do the same thing for the image of the particle I in the simulation box C, which is at the top layer, that is here. So, in this case you can see that this is the initial position, this is the peculiar velocity of the same particle in the box C, and here you can see that the y position is now added by a factor of L, because it is in the positive L direction, and then we multiply by delta t, and then now we are going to expand this. So, the first term is the initial position in the periodic box C, and then we have Ci C delta t, basically I am just splitting these terms up, and then we have the third term, which is due to the streaming velocity. This is because of this is a displacement because of the thermal velocity this is the displacement due to the streaming velocity. So, you can see that the displacement for the image at the top layer is little more than in the central simulation box. And then so from here what we can do is we split this up. If you look at this particular thing, so what is this? This is basically a time t equal to 0. We know that RIC is now nothing but RI naught plus y cap L. So, we are writing the events as such. So, now if you compare these two equations, this and this, you can write that the position of the ith particle in the top layer would be equal to the particle at central simulation box plus y cap L plus gamma L delta T x. So, what we are trying to do is we basically can look at this, we see that this term and then this term corresponds to Ri naught and the remaining terms are this. So, what we are trying to do here is after time delta t, the position of the particle in the periodic image at the top is basically given by the particle position in the central simulation box plus its y component because it is in the positive L direction, and then this extra amount that comes because of the streaming velocity. Similarly, we can also do for the periodic image in the bottom layer in the box G, image box G, and you will see that the y position is basically Ry minus L. And then if you apply the same formula here, you can show that the particle I in G image box corresponds to Ri of t minus y cap L minus gamma L delta x. So, this again is the displacement due to the streaming velocity in the bottom layer. So, why we have all this information is because if a particle leaves from the top boundary, a new particle comes from the bottom. And so, now we know that for the bottom layer the position would be Rig, and so the new particle position in the central simulation box after applying periodic boundary condition should be given by Rig, which is something we have derived here. Similarly, if a particle leaves from the bottom boundary, its periodic image has to come from the top, and then we already noted that the particle positions at the top is given by Ric, and so that is given here. So, in the normal equilibrium MD simulations, we could have simply used only these two terms by adding and subtracting the box edge length plus L or minus L. But now because of this additional shear effects and streaming velocities, we have to also change the x component of the positions accordingly. So, this is actually shown pictorially in this graph, in this particular plot, that if this is a particle and then if suppose if it leaves here and then we want to put back its image, and that would be coming from here to here, because by the time this particle goes here, its periodic image would have gone from here, and then now we put this back right here. So, in the normal situation this particle would have actually come somewhere here after moving, but because these particles are also moving to the left, so we have to adjust. So, that is what is shown here. If the particle leaves the top boundary from here to here, the new particle comes from the bottom, that is this particle, and the new position is obtained by Rig, that is Rig is nothing but the particle's position at the image box G, and that is obtained that we just now derived. So, this basically takes care of how to apply the the periodic boundary condition for the particle positions, but we also have to note the velocity should also be changed, because by the time the particle move there and when it comes here, the velocities have to be different. We can't have the same velocity, and in this case the Vig, that is the particle velocity here, would have been the particle velocity at I minus gamma L. So, gamma L would be the displacement that has happened over a period of time delta t along the x direction. So, we have to update the velocities of the particles also. So, this is quite different from how we do in equilibrium MD simulations. In the equilibrium MD simulations, we do not change the particle velocities. We only change the particle coordinates by adding or subtracting box edge length side it moves. Whereas in the non-equilibrium MD simulations, we have to do two things. One is that the particle positions have to be updated not only by periodicity but also by which amount it moves to the left or to the right. So that is taken care of by this term. Similarly, the velocities also have to be updated by knowing how much displacement or what's the rate at which these boxes are moving. Okay. So you can see that in this case, since the velocities are changing only in the Vx direction, we only change the x component of the velocity, keeping the y component, z component same. So if you do this, when we do this Lees-Edward boundary condition, when we apply them, essentially what we are trying to do is this as the simulation proceeds, modes might be escaping from the top and then coming from the bottom, and similarly the vice versa. So there may be particle crossing the lower boundary and entering from the top boundary. So when this happens over many iterations, then the particles velocities and positions are reassigned, and then if you wait long enough, you will see that the streaming velocity will be set up, a linear velocity profile will be obtained. What I mean by that is, if I look at the simulation box and then if I make a histogram of velocity distributions over many layers. So if I take all the particles in this cell and then all the particles in this cell, etc., and then if I plot the velocities, it would look something like this. And this is exactly the distribution that we want for the and this slope will be gamma, which is V by L. So this is something called imposing a shear flow through the boundaries. We are not really going to the molecular level and assigning, we are not adding anything to the Hamiltonian, we are not changing the equation of motion. No, all we are trying to do is we adjust the periodic, so the shear effects are basically sent through the boundaries of the neighboring imaging boxes. We are only saying that the boundary boxes are moving, the periodic images are moving at a particular velocity at the top from left to right, and then at the bottom from right to left, and then as the particle crosses the boundary over and over, they will feel this effect of the boundaries, and then the velocity will be reassigned, positions are reassigned. At the long time, you will see this kind of establishment of the steady state velocity profile, linear velocity profile. So once we have established that at steady state the linear velocity profile is obtained, then we can use this Newton's law of viscosity, get the pressure tensor as a time average, and then we know the imposed shear rate, and then from here we can get velocity. From here we can get the viscosity. And one of the drawback of this method would be that it takes quite some time for the steady state linear velocity profile to achieve, and it is not suitable for time dependent flow. So if you're looking at some external perturbation which are time dependent and you're looking at how the response are going to happen, then this method will not be very suitable. On the other hand, if you're looking at only a viscosity measurement by applying a small shear field, one can actually use the Lees-Edwards boundary condition as a method. So to summarize, so we saw that this non-equilibrium MD simulation can be used to study systems response apply an external perturbation. This external perturbation can be a imposed shear field, or it could be imposed temperature field, etc. And this response can be measured at a steady state. So for example, in the Lees-Edwards boundary conditions, the perturbation is the way that the periodic boxes are moving relative to the central simulation box. So that's the perturbation, and then here is what is the steady pressure tensor and the long time behavior. Once we know those responses, we can use some of the constitutive equations like Newton's law of viscosity or Fick's law or Fourier's law to calculate the transport properties. And we showed that the Lees-Edwards boundary condition is one simple method by which we can impose the perturbation through the boundaries and then measure the response and get the viscosity of the fluid.